We want to give you some information about the loading of the hip joint, typical levels of average loads and high loads, and this study was performed at the Julius Wolf of the Charité. There were several different goals of the study. It's a fact that the joint contact loads vary much between the subjects, from one subject to the next, and therefore fatigue and stability tests on hip joint implants, but also for fracture implants in the hip region, should not be based on individual load data as for walking, but more activity than just walking should be included in tests and analysis. So the goals of this study were that first, based on in vivo contact forces from 10 subjects during the most demanding activities of daily living, we calculated the average load levels for a subject with an average body weight, and that data set was called the AVA 75 data set, or the average 75 data set. And we also calculated the high load levels for a subject with a high body weight, and that data set was called the high 100 set. And we compared the average and the high loads with the test standards defined by ISO and used for fatigue tests on hip implants. And if necessary, we proposed more realistic test loads than defined in the ISO standards. For what can such standardized data about the loading of hip implants be used? There are test standards defined by ISO for testing the endurance of the implant neck. One more test standard defines the loads used for testing the stem against fatigue. But there are many other tests. For example, you can test the stability of the taper in modular implants, or the stability of implants which are used for neck fractures, so no joint implants, but fracture implants. You can test, for example, the torque resistance of cementless stems, and if movements data are available, which will be the case soon, you can test wear in the joint or the stability of the cup against moments, which is a real clinical problem. And you can also test the stress strain, or calculate the stress strain distribution and the bone remodeling around the cup, and also the remodeling around the stem. But both applications need additional the muscle forces, and they have to be obtained from analytical models. And you can also use the data for verify the outcome of musculoskeletal analysis in the hip region. So that was the instrumented hip implant we used for the measurements in the 10 subjects. It's a cut model, what you see, and we used 6 strain gauges. From the 6 measured strains, it's possible to calculate the forces acting on the head, and the whole implant was powered inductively. And the telemetry was used for signal amplification and for transmission of the signals via the antenna, which was placed in the head of the implant. And the head of the implant is made from ceramic, and the cup insert is made from polyethylene. What we measured were the 6 load components, 3 force components, and the 3 moment components in a coordinate system which was fixed to the femur, not to the implant. And the implant is rotated around 3 axes by 3 angles relative to the femur. That angle here, A V is the anteversion angle. So if you want or if you need the data relative to the implant, you have to make a coordinate transformation from the femur to the implant. That were the investigated 10 subjects. There were 8 male and 2 female subjects. And the age of the patients was 50 to 68 years. All measurements were taken between 10 and 19 months postoperatively. Here you see a typical measuring situation. The patient is standing on one leg, and you see the power coil, the red power coil around the hip joint, and a small antenna here for receiving the signals. That is all the equipment used for power supply and the receiver for the signals. And on the laptop here, you have a real-time control of what is happening at the same moment in the hip joint. And for our public database, all the patient activities were videotaped synchronously to obtaining the signals. That is the image that we can see during the measurements, and it's a typical example of one trial as you can download from the public database autoload.com. It first shows diagrams of the forces and moments. Here the green, blue and red forces are the single components, and in black you see the resultant force, and the scale is given in percent of body weight. So the peak value when standing up or sitting down is about 180% of body weight. A similar display was used for the moments, the 3 components in color and the resultant moment in black, and the scale is given in percent of body weight times meter. You can also see the force magnitudes and the force directions in the frontal plane, in the sagittal plane, and in the transverse plane. Additionally, you see the videos of the patient, and even more interesting for precise analysis are the numerical data which are displayed here in this field. This is a second example. The patient is going up a staircase, and you see that the force directions vary somewhat more than in the previous example, but they are still limited very much, at least in the frontal plane. That were the investigated activities. Cycling at 90 watt on a home trainer, standing up, sitting down, knee bend or squat, walking on level ground at an average speed of 4 kilometers per hour, the 2 and 1 leg stance, going up and down a staircase, and slow jogging on the treadmill at 7 kilometers per hour. How were the data evaluated? They had to be averaged. First, there were taken 6 to 20 trials per activity and per subject, and for averaging we used a procedure which was published by Benner and Bergman previously, and you see the curves here, the resultant force during walking. That's an example. The 20 trials from walking for the same subject, and the average trial, the typical curve for this subject here in red. And this averaging method was designed as to preserve the peak values in the curves from the different trials as good as possible. So that is the average peak value here, and that's also an average relative maximum. And if you would have taken instead the arithmetic mean of all the curves, you would, for example, have got a relatively flat curve here in the range or in the area of the maxima, and that peak value would not be representative for all the trials. For getting the average loads in a subject with average body weight, all the individual body weights were normalized to 75 kilograms, and then the 10 subjects were averaged using the same procedure as for the trials. That are the 10 subjects. You see the large variation between the subject doing the same activity, which was walking, and you also see the average curve here from all the subjects. So that's an average subject with an average body weight of 75 kilograms, and that data set was called AVA 75 or average 75. But for testing the endurance or strength or stability of the implant or of its fixation, higher load levels are of more interest, higher load levels as they can be observed in some of the subjects. So we determined the high 100 loads in the following way. We first took the AVA 75 data, that are the black curve here in the example from walking. We identified the peak values of the different subjects here. We determined the highest peak value here. That is the peak value of one subject which was higher than all other subjects. So we took the AVA 75 data, increased it to that peak value. We furthermore increased the body weight from 75 to 100 kilogram, and there was a certain amplification factor here, and all the averaging procedures were made using the resultant force, but that amplification factor was then applied to all load components. And that are then the high 100 loads. They are representative for the highest load levels observed if the patient had a high body weight of 100 kilogram. The six forces and moments, the 6 components, were therefore determined for average body weight and average load levels, and for high body weight and high load levels. And you see here the high 100 loads for the different activities, 9 different activities of daily living. And the example here, the red curve, is the curve from walking with 2 peak values shortly after heel contact and shortly before lifting off the foot from the ground. In the following, the data presented in this talk represent the high 100 forces and moments, because these high load levels are more critical when testing endurance or stability of the implant or its fixation. And all loads presented here are given in a femur-based coordinate system, and for transforming them to the implant system, you need to perform transformation of the loads from the femur to the implant system. Again, the high 100 loads are shown over the whole loading cycles for the different activities. Let's have a look at the activities and the peak values during the 9 activities. That are the total load, 100% of a load cycle, and that is the peak value as observed when the patient cycled on a bicycle trainer, so the force is very low. That are the forces when sitting down, standing up, and knee bend, and that is the peak value when the patients were walking on level ground. And you see there are some of the activities which were performed on 2 legs, namely knee bend and especially standing up, when the forces were higher than during walking. Also, the activities were performed on 2 legs, so the total load could be distributed between the 2 joints. Higher load than during walking were observed when the patients were standing. So on average, when standing, the forces are higher than during walking. And the highest forces from all activities were seen when going upstairs, and even a little bit higher when going downstairs. And certainly the highest forces were observed during jogging. So you see the forces are close to 5,000 Newton, or 5 times body weight than when the patients were jogging at a low speed. So at a higher speed, the forces will even be much larger than 5,000 Newton. The highest forces were acting when going down a staircase, and certainly when jogging, and both values were much larger than during walking. And let's have a look at the activities with double leg support, which are sitting down, standing up, and knee bend. And you see, especially when standing up, the force is much higher than during the 1 leg supported activity walking. It seems a little bit mysterious that the forces are so high when you are standing up, much higher than during walking. And so I will explain you in the following how that comes. As shown already, the high 100 loads are based on the average, that are the average load displayed here. During all the different activities, and the high 100 loads are based on the highest peak value of any of the subjects in the average load. So that are the data from all the subjects after the body weight had been normalized to 75 kilogram. That's the average subject. And you see that the curve for subject number 5 is much higher than for any of the other subjects. So the reason for that was that patient number 5 had pain in the contralateral joint, so the subject shifted the body weight to the ipsilateral side where we took the measurements. And because the absolutely highest peak values were used for calculating the high 100 loads, that's the reason that for these 3 activities, and especially for standing up, the high 100 loads are much higher than during walking, for example. But we decided to leave that data in the data set because it's not uncommon that patients obtain a new hip joint and still have pain in the other leg for a long time. Next thing what I want to show you are the directions of the forces throughout the whole loading cycles for the different activities. That are the 10 or 9 different activities. And during the whole loading cycles and during all activities, the direction of the force is always positive. That means it acts from medial to the lateral side of the joint. And a similar finding was seen if you have a look at the anterior posterior force. It is always negative. So this force always acts from anterior to posterior. So in general, the forces always, there's are two small exceptions here, but in general, the force relative to the femur always act from medial and from anterior. If we make the same kind of analysis on the moments, we get quite different results. That is the moment mx during the whole loading cycle for the different activities, and you see that the sign of the moment mx changes throughout the loading cycle, so it is positive here in that area, and later on it's negative, and it's the same for all activities, positive here and negative here. And the same observation was made for the moment my, so it also changes its sign from positive to negative, and for all activities observed, and exactly the same for the moment mz. So the moments, all moments in all three planes permanently act their sign. They are positive and negative depending on the location during the loading cycle. The next thing I want to show you is an example from walking, and it shows you how the load direction, the force directions during one cycle of loading change throughout the loading cycle. So that is high 100 data, the average data during walking. And the red curve is the curve how the force vector moves throughout the step. Walking started here in our example. That is the first force vector from the red curve to the center of the implant. And if you start walking, the force increases until it reaches its peak value. And what you see is that the force directions here are very similar throughout the whole loading cycle. So there's an angle between 13 and 20 degree relative to the long axis of the femur, and that small range between 13 and 20 degree is valid if the forces are higher than about 50% of the maximum. If the forces are lower, here the force directions are more oblique, but these small forces here are not so important for testing hip implants. So the high forces and their limited range of direction is most important for testing the. That's one more example from jogging on the treadmill, in this case at 8 kilometers per hour. And you see if the force magnitudes are high, here the force directions are very close throughout this part of the loading cycle, and the more oblique force directions are only valid for small forces. Until now, we had a look at the force directions and the close range of force directions during one cycle of a given activity. Now we will have a look at the peak magnitudes for the different activities. The high 100 loads are shown here for all activities, and data are given for the frontal and the sagittal plane. That is the peak force during walking, the average peak force. That are the peak forces from the 7 activities of daily living, except jogging and cycling. And if you have a look at the load directions for the different activities, here, you see again that the peak values act under a very similar direction. So they act under 15 to 24 degree. That are the directions of the high 100 forces in the frontal plane and in the sagittal plane. So you see in the sagittal plane the range of force directions between 4 and 18 degree is much higher than in the frontal plane, 15 to 24 degree. So how do these in vivo forces during the different activities compare to the ISO standards which are defined for testing the endurance of implant stems and necks? That is the endurance test for hip implants, for testing the stem of the hip implant. So the lower part of the stem is embedded only, so we test here that area, the stability of that area of the stem, and the peak force is 2300 Newton under a given direction. And a similar test is described here by the ISO standard for testing the neck. In that case, the stem is embedded over its whole length, so that area of the neck is tested, and the peak value of the force is much higher, 5340 Newton. So now we have a look how the magnitudes and the directions of the ISO tests for testing the stem and the neck of the implant compare to the real in vivo loads. You see that obviously the magnitude of the ISO stem force is much lower than the magnitudes for 7 of the activities, and even much lower than the force during jogging. So even for walking, the ISO test magnitude should be increased by at least by 20%, and much more when simulating all the other activities here. And the ISO neck force here obviously has a magnitude which is much higher than during the 7 activities and even higher than during jogging. So the magnitude of the ISO neck force is high enough. But obviously the direction here in the frontal plane of both ISO test forces should be adapted to the real situation. So the direction should be somewhere here in the middle at around 20 degree instead of 9 degree. The direction here in the sagittal plane fits the in vivo data much better. It lies, the 6 degree are between 4 and 18 degree. So that are the in vivo forces as shown already for the different activities, and added are the forces for the ISO stem test and for the ISO neck test. And as seen before, the peak values of the ISO stem force are much lower even than during walking, and much lower than, for example, when going down a staircase. And again, you see that the ISO force defined for testing the neck is high enough, the amplitude is high enough. So even compared to going down a staircase, there's a safety factor of about 35%. So what's the best way to choose a realistic test force? And the first question is is it justified only to use the contact forces and to neglect the friction moments when testing hip implants for stability of the stem? That's mainly addressing testing the stem. And so what we saw and what has been published, that during near all activities, the forces in neck and stem of the implant, so at the local point at the stem or at the neck, they increased by less than about 3% when the friction moments were added to the contact forces. So very obviously the friction moments can be neglected when testing the stability of the stem. They cannot be neglected when testing the stability of the cup. So how to choose the most realistic load? So we have the in vivo forces, we have the ISO standard test forces, and possible test forces can be, for example, one force like acting in vivo from walking, a certain force which is comprised from the three most demanding in vivo activities. One could apply all 7 forces from the in vivo activities except cycling and jogging. There was another idea on which we worked, that was to use the most oblique forces, which we called the pyramid forces. That are the forces which act under a most oblique direction relative to the long axis of the femur or of the implant stem. And then you can choose between the 2 isoforces and the 4 pyramid forces, and have a look which one causes the most realistic test conditions. And I will also present you a new concept to find the optimal test force for testing the stability of the stem or the neck of the implant. And you find the numerical data for most of these test forces at the end of the presentation. So you could apply one force as during walking in vivo, and the amplitude is 2800 Newton. But as we have seen already, that force is much lower than during many other activities of daily living, even if you exclude jogging. In general, 10 million cycles of the test load would have to be applied for fatigue tests. The next idea was to use data and peak loads as they act during the 3 most demanding activities. And that is the results, and that force was taken from walking, from going down a staircase, and from knee bend, but with the different cycle numbers: 20 cycles of walking, 2 cycles of stair down, and 1 cycle for knee bend, and all the 23 cycles were averaged. And you see that the direction of that blue force and also the peak value here from the 3 most demanding activities, they are very close to the direction at the peak value from walking. So that's not a real better test force compared to the forces just only during walking. A very realistic way of testing hip stems and hip neck would be to apply 7 forces from all activities, with jogging and cycling excluded, but you would have to apply different cycle numbers to simulate the real situation of the patient. So the relative number of cycles is 20 cycles for walking, only 2 cycles for going up and down a staircase and for stands, and only 1 cycle for sitting down, standing up, and knee bend. And this relative number of cycles for the different activities was taken from the literature. And then you can apply loads as during all 7 activities, and you apply sequences of forces, and each sequence would consist of 1 million cycles, and within each sequence you would have to apply 700,000 cycles of walking, and then 70,000 cycles for going up a staircase and so on, and only 35,000 cycles for sitting down and so on. And after applying one sequence, then you would have to apply the other 9 sequences until you reach 10 million cycles. Now I want to present you a new idea. So if you want to test fatigue, for example, or the strength at a given point at the neck or at the stem of the implant, the bending moments and the torque at the given point of interest are most decisive for the local stresses. And the local stresses decide about the fatigue and the strength at this location. And these bending moments are largest if you apply those forces that are all the in vivo forces we have measured from all activities and all subjects, and that are the most oblique force direction relative to the stem axis or to the femoral long axis. And the bending moments are largest if, in most cases, are largest if the forces act under the most oblique directions. How to calculate the most oblique forces. These forces were called by us pyramid forces, just to have a name. And the concept is that for all activities and subjects, we use the individual force directions from the single subjects from all activities, and we looked for the most oblique force direction ever observed. And then we identified the 4 pyramid forces, which are most lateral and anterior. So that is the most from the anterior side, and from the lateral side, that is force FLA, lateral anterior force. And we also define 4 more forces at the most oblique force directions. So, and finally, what we did is to set the amplitudes of all forces to the highest amplitude, average amplitude from all activities. That are the high 100 forces when going downstairs, and that is 3,606 Newton. The small symbols you see here are the individual peak forces from all subjects and all activities. For example, when going down a staircase, one subject has this peak force, the next has this peak force, so there are different magnitudes and orientations of the peak forces for the different subjects. For all subjects and all activities except cycling and jogging. And you see that for the activities, for example, stairs up here, there are different orientations of the peak forces or inclinations of the peak forces relative to the long axis. So one patient has this inclination of the force, the next subject has this inclination of the force. And the extreme force directions were calculated as I explain you now. So we took different numbers of activities as shown already, 20 cycles of walking, 2 cycles stairs up and so on, 1 cycle of sitting down. And then we calculated the inclination in both planes. So the inclination of this set of activities. We determined the 5% percentile of the inclination and the 95% percentile of the inclination in both planes, in the frontal plane and in the sagittal plane. And from this data, from these orientations here, we then calculated the 4 pyramid forces. After having determined the percentiles of the inclinations into planes, we defined the 4 pyramid forces with the names FLA, FLP, and so on. So the directions were taken from the percentiles, and for giving one example, the force FMP is the force acting from the most medial and most posterior direction. And furthermore, we calculated the central force in the middle of the 4 pyramid forces. So in this way, we knew the direction of the 4 pyramid forces, but we don't know the amplitude. So we have to decide how high the amplitudes of the 4 forces should be. For this purpose, we use the high 100 amplitude from going downstairs. That is the highest amplitude from all activities. And we assume that to be the amplitude for all 4 pyramid forces. In this way, we finally also got the magnitude of the pyramid forces. So that are the 4 pyramid forces in the frontal plane and in the sagittal plane. So there are 2 different possibilities to apply the 4 pyramid forces. You can define a force with the amplitude of, let's say, FLA, and make a sine-shaped curve with a certain minimum, and apply one force after the other. For example, each of the forces with a number of 10,000 cycles, and until you have reached a total of 10 million cycles. For that, a unidirectional loading machine would be sufficient, but the implant would have to be rearranged between the sequences, which is unfortunate. The second possibility would be to add a central force of 200 or 300 Newton, and to apply one force after the other by continuously changing the load magnitudes and directions from one pyramid force to the next via the central force FC200. So you apply such a time pattern of loads. And this, however, would require a 3D loading machine, which is not always available. Until now, we have the 2 ISO test forces, we have the 4 pyramid forces, and we have the 7 in vivo forces, except cycling and jogging. And now we have to decide which of the ISO forces and the pyramid forces is best suited for testing the implant. For example, at these 2 points of interest at the base of the neck and in the middle of the shaft. And the internal loads determining the stresses at the local points of interest are the compressive or shear forces, but also the bending moments and the torque here at the points of interest. And for stresses in the implant, in most cases, not always, but in most cases, the bending moment and the torque are most decisive. the question is there any of the four pyramid forces or the two isoforces which produce higher bending moments and torque at the selected points of interest, either in the neck, somewhere in the neck, or in the stem? In our case, we calculated it for the base of the neck and for the middle of the stem. So, is there any of the six forces which produce higher moments than ever measured during any of the investigated activities when cycling and jogging are excluded? For determining the local bending moments in the neck and in the stem, we use the high 100 forces from 7 activities, the two isoforces and the 4 pyramid forces, and transformed all that loads to the coordinate system of the implant. And for that, we use the size and the orientation of our implant, of the average from all subjects, and that average of subjects had transformation angles as x of 4.5 degree in the sagittal plane, as y of 1.4 degree in the frontal plane, and an angle of 12.5 degree in the transverse plane. That's the anteversion of our average subject. So then we calculated the moments in the local coordinate system. You see they are transformed. The long axis of the neck is Z, and the long axis of the stem is now the axis Z. And we calculated the total bending moments here around the axis, which were taken from the components mx and my. So we calculated the total bending moment, and also calculated the torque along the long axis. So what we got out was, for the bending moment in the neck, for the different activities here, from sitting down to going down a staircase, that were the bending moments. And the highest bending moment was observed when going down a staircase. And this bending moment, the highest level of bending moments during stairs down, is the horizontal line here. And that are the bending moments which are caused by the two isoforces and the the 4 pyramid forces. So obviously bending in the neck is much too low if you apply the iso stem force, but it is very high if you apply the iso load, which is defined for testing the neck. And there are two of the pyramid forces which produce sufficiently high bending moments in the neck. The torque in the neck is always 0 because we neglected friction. In the same way, the bending moments and the torque in the stem were investigated. So the highest bending moment acts if you are going up a staircase, not when going down the staircase. And when going up a staircase, the bending moment in the stem is at this level. So, and we add the bending moments which are produced by the iso loads and by the 4 pyramid loads. And again, you see that the iso stem force is much too low, much below this level here. The iso neck force is high enough, so much higher bending moment in the stem than during any in vivo measurement. And there again, there is the force FRA, which produces moments higher than during any in vivo activity. And the torque, there's a similar picture. The torque is highest when going up a staircase. That is the level, the highest in vivo level, and that are the isoforces and the four pyramid forces. And again, you see that the iso neck force is just high enough. The iso stem force is much too low, and the pyramid force FLA is sufficiently high to simulate the highest torque observed during any in vivo activity. Which forces produce higher moments in neck and stem, than measured in vivo during any activity? So we calculated the safety factors in neck and in stem for bending and for torque. That are the activities which produce the highest moments, going downstairs and going upstairs, and that are the safety factors if you apply the iso neck force. The safety factors are between 61 and 0%, and the pyramid force FLA always has positive safety factors between 15 and 27%. Even the iso neck force has a safety factor of only 0 regarding torque in the stem. The iso stem force, as seen already before, produces always bending and torque which is much too low, so the safety factors are negative. So the pyramid force obviously is best suited to test neck and stem in a most realistic way. That force, FLA, produces bending and torque in stem and neck, which is higher than during any other high 100 activity. To summarize the results of this study, it can be said if you want to use a unidirectional test force for testing either the neck or the stem of the implant, the either neck force or the lateral anterior pyramid force FLA should be applied, where the pyramid force FL is most realistic. It simulates the highest moments in neck and stem of the implant, highest from all high 100 activities. In general, the iso stem force is much too small for testing the stem or the neck of the implant. If a multidirectional joint simulator is available, you can apply a mixture of real forces as during daily living with a different number of activities. That means much more activities or loading cycles from walking than for the other activities, or you can apply a sequence of the four pyramid forces. Both are realistic test conditions, but what must be said is that the optimal test force FLA may be different if other points of interest that are chosen on the neck or stem of the implant. So the calculation of the moments was performed for the lowest end of the neck and exactly for the middle of the stem. There's one important remark, namely that additional safety factors, as they are usually applied in fatigue tests on technical equipment, such safety factors were disregarded when proposing the 7 in vivo forces, the 4 pyramid forces, or the force FL as test forces. So for the sake of security, all these forces should be increased by a certain factor to improve the safety of the implant. And the second thing is that if the in vivo or the pyramid forces are used for testing stability or wear of the cup, the movements between stem and cup are additionally needed, and they will be published in a short time. So the last concept I want to present you is to find optimal test force, which is even better suited for testing the implant than the pyramid force FLA. That is work in progress. So that's not finally finished, that project. You select a point of interest at the neck or stem of the implant. You apply all measured high 100 forces from all activities and all subjects, and you calculate the 6 forces and moments which are caused by the contact forces, and you determine the extreme values of all 6 components. And finally, you use the implant cross-section and dimensions and position and so on, and you calculate the stresses, not the moments and forces at the point of interest, but the stresses. Then you identify those 3 of the 6 extreme loads which cause the highest stresses at the point of interest. In most cases, that will be the 2 bending moments and the torque. So you have 3 knowns, the highest values for My, Mx, and for Mz. There's one possibility where not the 3 moments are most decisive, but for example, if you want to test the torsional stability of the stem in the femur, the longitudinal force Fz minus Fz, which presses the implant into the bone, will be decisive for the moment Mz used or required for loosening the implant. So now you have a mathematical system with 3 known variables that are the maximum moments, for example, or the 3 of the 6 load components acting at this point. And you have the optimum force, which has 3 unknown components, so you can solve the system and you can calculate the single force F optimal, which exactly produces the selected 3 extreme moments or 3 extreme load components at the point of interest here. And the force F opti will then produce stresses at the point of interest which are as high as the in vivo maxima seen from all activities and subjects, and the optimal force will then be a sine-shaped force with the amplitude F opti and a minimum in between of, let's say, 200 or 300 Newton. And that is work in progress, as I've told you, but at the moment we are developing a computer program for determination of F opti. So with that, I want to thank you for your interest. I want to thank all my co-workers which worked with me for many years, and Philip Damm here, he is in charge for the hip. And I also want to thank those institutions which have financed this study over many years. So, something about the data and so on. This talk was based on data from this publication here with the same title as the talk, and that has been published in PLOS ONE in May 2016. You can use any data and images from this talk with the proper reference you have to make, and maybe you stop the video and have a look at the reference for using the data for public purposes. If you want to get data or videos of the patient activities from the data which were used for the publication or for this talk, you have to go to the public database autoload.com, and there you select hip joint 3 as the type of implant, and you furthermore click on gait analysis and choose one of the activities like cycling or jogging or going up a staircase and so on. So that is a source for single trials which were used for the evaluation of data as in this talk and in the publication. If you are more interested not to get data from single trials, but to get summarizing diagrams from all the subjects or numerical data for the average and the high loads, you can also have a look at the autoload.com database, and you choose there test loads, and again standard loads hip 3. And there you can download huge data sets with all the diagrams and the numerical data. Finally, you find a list of possible test forces, and that is data load data relative to the femur system, the resultant force as during walking, the components, the resultant force, and the directions in the frontal and in the sagittal plane. The next is method number B. That is the force calculated as a mixture from the 3 most demanding activities. That is method C. That are the 4 pyramid forces here and the central force. The components again, and the directions in the 2 planes, and that are the ISO test forces defined for testing the stem and the neck of the implant, and all that are data defined relative to the femur system, and the most realistic single test forces are FLA and possibly the ISO force for testing the neck of the implant. The same data is given here relative to the implant system. So that are all forces acting in the implant system, and for recalculating the data from the femur to the implant system, the 3 transformation angles alpha x, alpha y, and alpha z are used. So alpha z 12.5 degree is the average anteversion of all our subjects. So the same kind of data here, but this time relative to the implant system. That's the end of the talk. I thank you very much.